This is a review of some diagrams that you might be asked to draw. So I've given you some examples. I've tried to think of things in a different way as to hopefully prepare you if you're asked to draw something other than a graph on free response. So again, solutions or some kind of reaction, that has been asked before on the AP exam. If they're not asking you to draw it, you'll have to recognize this and answer questions about it. So, we know solutions are designated as aqueous. You see the AQ symbol. And again, this could be maybe a soluble ionic compound. And we know it's, our solubility rules, group 1 ions, nitrate, ammonium ions are soluble. When we have something like this and we're asked to write net ionic or recognize it as net ionic, we would have separate ions. Also with strong acids and bases, and they're the 6 strong acids, and the most common strong bases are group 1 ions with hydroxide ion. Again, those are completely dissociated in solution. They're strong electrolytes. We would write those as separate ions as well. It's when we have weak acids and bases where we write the whole molecule, or you would have to recognize it as written as the whole molecule in solution. So here's a picture. What 2 solutions were mixed together that resulted in the species in the beaker? So it's kind of working backwards. This was actually an answer to a multiple choice question where they told you in words a reaction. I was just trying to think of how this could be asked differently. So you notice there's a precipitate, AgCl, so kind of work backwards from that. And then the other question is, what is the net ionic reaction occurring in the beaker? And then which solution must have been dilute and in excess? So start with trying to come up with a double replacement reaction. So what would have been the 2 solutions that were mixed together? If we end up with AgCl, AgCl could not have been one of them because it is a precipitate. So we would have to have Ag ion with something, and we'd have to have the chloride ion with something else. So hopefully you'd figure out that it would have to be sodium chloride and silver nitrate. So from that, thinking of that double replacement reaction, come up with the net ionic. And then which solution must have been dilute and in excess. So again, look at the beaker, what's not in the picture as an ion, and that should help you come up with which of your solutions is dilute. Because if you can see from the precipitate, it has silver ions that came out of the solution to form a solid, and the chloride as well. Notice there's still chloride in the solution, so that should give you a hint. So here are your answers. The 2 solutions were silver nitrate and sodium chloride. There's the net ionic. The net ionic only includes the ions that are actually reacting, and in this case forming a precipitate. And you can see that the sodium ions and the nitrite ions are just floating around as spectator ions. They're not in a reaction, so they do not need to be included. Silver nitrate was dilute since there was no silver ion left in the solution. We do see a nitrate ion since it is a spectator. Sodium chloride had to be in excess since although chloride was part of the precipitate, there's still chloride left in the solution, and then we see twice as much sodium ions. So, redox reactions. Right here are 2 pictures. Write a balanced half reaction that occurs in each cell below. Which half reaction would be oxidation, which is reduction. Notice in the left picture you see it's copper 2+, and you have copper, which this is supposed to be, that is the metal electrode, and over here we see the zinc electrode and then the zinc ions in the solution. You can tell from the arrows which way this is going. In the past they've asked students to show how spectator ions are moving through a salt bridge, and so I was just trying to think of how else they could use a particulate diagram to talk about redox. So think of the half reactions. You should see that the copper 2+ ion is gaining 2 electrons to form solid copper, and that the opposite is happening in the zinc side. The zinc is losing 2 electrons and forming zinc 2+ ions. Also note that the metallic ions in the solution are smaller than their than the copper on the copper electrode and the solid zinc on the zinc electrode. If you were asked to draw this, the size would have to be different, okay? Because when they're losing 2 electrons, now the remaining electrons have a greater attraction because the number of protons haven't changed. So the effect of nuclear charge is the same, yet there are less electrons they need to attract and fewer electron-electron repulsions. So the copper is reduced, copper 2+ ion is reduced, and the solid zinc is oxidized. Okay, so draw 4 molecules in the boxes, and I've given you Br2 liquid goes to Br2 gas, and then same directions in the second one. Br2 gas goes to Br gas. Okay, so for my liquid, I just represented it as, I didn't ask to, show any kind of IMF, like anything holding it together. However, these are diatomic molecules, so you'd have to have the 2 atoms together and, slight organization as the liquid kind of filling the bottom of the box. As it becomes a gas, all that should happen is that they're separated. Hopefully that shows that they're kind of floating around or moving around as a gas. And then number 2, draw 4 molecules in the boxes. So again, we've still got this. This time we're starting off with the gas, and then notice it went to 2Br. So that meant that now we have separate atoms. And so if we had 4 diatomic molecules, that's 8 atoms total. We should have 8 separate atoms in the right box. So the next question is, what is happening in each process? So I'm trying to get you to think about, are bonds being broken, or IMFs being broken, and if it's an IMF, we need to say specifically which one. So notice liquid to a gas, that's a state change, that should help. And then here you can see just the formulas itself look different. So hopefully you would come up with LDFs are broken, since diatomic molecules would be nonpolar. That's the only force of attraction between them would be their London dispersion forces as they change states. And then when we go from Br2 to 2 separate atoms, the internal covalent bond had to be broken. So again, here's a little bit more with IMFs. Draw and name the IMF that would occur between, and then the first one is ICl. So I said draw 2 of those and show how they would be attracted. And then draw how an ammonia molecule would be attracted to water. And then the last one, draw what NaCl would look like in water. I didn't really give any specifics on that third one. I just wanted to see, I would probably draw at least 6 water molecules, 3 with each ion. You could draw more. If this was an AP question, it would be extremely specific, and they'd probably only ask you to draw 1 of the ions with water. The calcium ion surrounded by water was on a previous AP exam. So notice ICl and ICl, it's very simple molecules with just 1 single bond between them. However, since iodine, chlorine's really close to fluorine and iodine's further down the group, you would expect that to be a polar bond, since they're not right next to each other. And if they're both polar molecules, which you can see is designated by the partial charges, again, if you added the charges and they weren't partial, it would be incorrect. That dotted line in between is the dipole force of attraction. They don't have the right components to have hydrogen bonding, so it would only be dipole-dipole. There's ammonia and water. Notice they did space-filling models, which don't show the lone pairs, but remember the nitrogen does have 1 lone pair, and oxygen has 2 lone pairs. So if you did a Lewis structure, you would show the lone pairs, but if you're asked to draw a space-filling model, those aren't included typically. So that would be a hydrogen bond, because we have a hydrogen on the oxygen that's bonded to a very electronegative element, oxygen. So that makes that a very polar, and then the shape gives it that overall dipole. So hydrogen has a pretty strong partial positive charge. And then nitrogen is very electronegative, so it has a strong partially negative charge, so that dotted line, which is representing the hydrogen bond, is that IMF attraction. Now, NaCl water, notice that chloride is larger than the sodium ion. There should be the two ions would have to be totally separated. There are a lot of water molecules drawn around each one. The most important thing is that the hydrogen end of the water is pointing, because it's partially positive, pointing towards the negative ion chloride, and then the opposite's happening with sodium. Since sodium is a positive ion, the partially negative oxygened end is pointing and very attracted to the sodium ion. If you were drawing this and you had your water molecules touching the ion, you would still get, it would be full credit. You just have to make sure all waters are pointing the correct direction. Typically they haven't asked for these partial symbol. For you to designate, the partial positive and negatives on water or anything else. But again, if you feel the need to write these, if you haven't been asked and you do not put the partial symbol, you will get no credit. So don't say water has a positive and negative end, because it does not. It has a partially positive and a partially negative end. It's extremely important. And even if you're saying the correct information, that will undo what you're saying that is correct. All right, acids. Which of the following is a strong acid, which is a weak acid, and how would we know this? So I've given you the key as that is supposed to be a hydronium ion. So, you can tell the center is the oxygen, and then it's got these three hydrogens attached, and it's overall positive. So notice in the first picture, we can see, we don't have a key for this other molecule, but you can tell that the small dark sphere must be the hydrogen, and then the other, gray sphere would be some other nonmetal ion, like a fluoride or, something like, maybe this is HF. That might be a good example. So we could tell figure 1 is a weak acid, mostly in the solution. It has the bonded molecule of the acid, and it only has, the one hydronium ion and the one fluoride, and we could tell figure 2 must be a strong acid. There's not one molecule in there that's bonded together. All of those have been ionized and separated. You could be asked a question here, and there's the answers on the next slide. Which of these would have the lower pH? We would pick figure 2 because it's a strong acid. It has all these hydronium ions in the solution. You could ask which one. I don't know if they'd ask a Ka question here, but obviously the Ka of the weak acid, figure 1, would be very small. The Ka for a strong acid would be very large. Just different questions like that. Titration curves. Which of the following pictures matches each point on the curve? You have to really think about, at point A, there are 4 points listed, 4 pictures, so there should be one for each. What's going on at A? So, look at your x-axis. That's what's in the burette that's being added. So A is at 0 sodium hydroxide, so it must be just the acid. We can see it's a very low pH. So if we look at the pictures, we should be looking for just acid. Notice all the water molecules have been left out for clarity. So looking at the pictures, come up with your answer. And then at point B, you've had sodium hydroxide has been added to the solution. So think about what's happening as this reaction takes place. You had acid, you're adding a strong base, so some of that acid is going to react with and neutralize all the OH minus that's being added. And then you get to C, which is the equivalence point, which really all you have at C are products. So think about what picture makes sense there. And then at point D, think about what must be making that pH really basic. So hopefully you came up with, at point A, you should have picked picture 4 because you can see it's H plus and Cl minus, and they're completely separated, so that means that's a strong acid. At point B, since we added some hydroxide, again they don't have many molecules, so they let the hydroxide react with one of the H pluses. So notice where there's one H plus remaining. Still 2 chlorides since it's a spectator, but now we have to have a sodium ion show up since we've been adding sodium hydroxide. At point C, you should have pictured 2 because all we have are products. If we've left out water, all we would have is dissolved sodium chloride. The 2 reactants, H plus, are gone. They've been completely neutralized with the OH minus that's added. And then at point D, it would have to be picture 3 because the reason the pH is so basic is because we keep adding hydroxide ion. Notice there's more sodium as well, and there's no more H plus to react with it because at point C, all the H plus that was present was completely neutralized with the OH minus that was added. Okay, so then we get to this other titration curve. Notice we can tell from the beginning this is a weak acid. If we look at the pictures, we can see CH3COOH, which is acetic acid. If you just kind of look around at the keys, you have to kind of watch these closely. Notice that red oxygen that has a hydrogen attached here and here. That is the acidic hydrogen. When you have an acid that has oxygen in it, the hydrogen that makes it an acid will always be attached to the oxygen. So notice that's why they're writing the formula that way instead of totaling everything up, because that last hydrogen is the acidic hydrogen. And so notice acetate that's pointed out there just has those 2 red oxygens. That hydrogen that was on one of them previously is gone. Alright, so looking at point A, notice there are only 4 pictures and there are more points to find. So really, we would look at there's a picture for point A, C, E, and F. So go ahead and make your decision. Okay, so at point A, it would be just the weak acid. We only have 2 molecules, so they both have to be intact. Since this is a weak acid, we'd write the whole molecule. Notice we can tell there's the OH, that's the hydrogen that makes those 2 an acid. As we start adding hydroxide, those hydrogens, are reacting with the hydroxide to make water. So it leaves us with acetate, and so this is our acetate. So at point C, remember the buffer is equal, so we have 1 acetic acid and 1 acetate, and then it shows that 1 sodium ion showed up as well. To show points B and D, we'd have to have more molecules in the picture. So if I started with 4 acetic acid molecules, then at point B, I would have like 3 acetic acids and 1 acetate. At point C, I would have 2 acetic acid molecules left and 2 acetate molecules. So at point C, it has to be even for pH equal pKa. And then at point D, if I had 4, it would be 1 acetic acid left and 3 acetate ions formed. So again, our pictures are a little bit, it just gets complicated with all these drawings. So they've kind of simplified it. But so we have point A was picture 3 from before, point C is picture 2, and then we get to point E. Remember, the products control the pH at the equivalence point, so all we can have there is acetate and then our spectator ions of sodium. And then at point F, we should have picked picture 1. That's the first time we see the hydroxide ion present in the solution, and the reason it can build up in the solution is because at point E, the equivalence point, all the acid that was in the solution was reacted, and there's no more there, so we keep adding hydroxide, and that's why the pH ends up going up so high.